So I mentioned super pollutants and short-lived climate pollutants. Here they are. So the response time to mitigation efforts and the anthropogenic sources are important here. So the substance is black carbon, methane, tropospheric ozone, and hydrofluorocarbons, the new refrigerant that replaced CFCs after CFCs were found to be causing the ozone hole. But now it turns out that HFCs are actually very long-lived and they have huge global warming potential. We'll see what that means. Okay, so there are various sources like cooking, industrial activities, driving, power generation, and methane comes from cattle and livestock, wetlands, rice paddies, methane burning, oil burning, and trash, right? Landfills and so on. And tropospheric ozone as well comes from various sources like imperfect burning of the fossil fuels in transportation, and hydrofluorocarbons, of course, from all sorts of refrigerants and aerosols. Lifetimes in the atmosphere: black carbon just a few days, methane has order a decade, and tropospheric ozone a few weeks, and the hydrofluorocarbons 15 years weighted by usage. Okay, so this can actually be much longer. The impacts: black carbon doesn't transport very far because its residence time is very short. So it's generally local, whereas methane is much smaller at local scale but much larger at global scale. In a decade it can make a circle. Ozone similarly is mostly local with some global impacts, and HFCs hang around so long that they are mostly global impacts. Okay, this is important because we refer to as super greenhouse gases the gases which have much higher global warming potential. What does that mean? If you take carbon dioxide, the main greenhouse gas, as having a global warming potential of 1, so you look at per unit increase in CO2 over a certain period of time, how much warming it causes, and then you compare all the other greenhouse gases to that. Okay, so the methane residence time is already, as we said, around 12 years. It's highly oxidizable, so gets converted to carbon monoxide and then carbon dioxide, but it hangs around for about 12 years. Its global warming potential over 100 years is 30 times that of CO2. Okay, it's 30 times more powerful as a greenhouse gas over a period of 100 years compared to carbon dioxide. So we have to worry about the concentration, the residence time, and the global warming potential. Those are the three things that determine how much they contribute to the warming. Nitrous oxide has a very long residence time of 114 years, still shorter than CO2, but nonetheless that's pretty long. Its global warming potential over 100 years is 298 times. That's almost 300 times that of carbon dioxide. But what we didn't mention here is that we measure CO2 in parts per million by volume, whereas methane and N2O tend to be in parts per billion. So this is right now of the order of 17 to 1800 parts per billion, and N2O is around 300 or so parts per billion. So their concentration is much smaller, but you can see that their global warming potential is much larger. HFCs, there are multiple ones, have a residence time of 14 years when weighted by usage, but some of them can hang around for centuries, and its global warming potential over 100 years is 1430 times. So that's also incredibly potent as a greenhouse gas. Okay, so for the future, it's clear that HFCs have to be replaced because it's just too damaging as a greenhouse gas. We replaced CFCs with HFC because CFC was causing ozone hole. HFC was readily available, agreements were quickly made, ozone hole and the UV that it allows to come in is bad for everybody, so there was going to be no winners in that situation other than the people who sold HFCs. But now HFCs are tremendously harmful as a greenhouse gas, hence they have to be replaced, but we don't know exactly what will replace it, and this leads to many other questions. For example, a country like India or China, where it's getting hot, people want more and more air conditioners and refrigeration, and as they get richer, GDP grows, economy grows, they can afford more air conditioning and refrigeration, which means they contribute to global warming as well. So whoever finds a replacement to HFC has to decide how they're going to sell it to the countries like India and China, unless India and China invent the replacement, right? So the summary of scientific consensus on various aspects of global warming and climate change is the atmosphere getting more polluted? Yes. Are the greenhouse gases, CO2, methane, and others increasing? Definitely. Some of them can be measured precisely and accurately because they are long-lasting and well mixed, whereas shorter-lived greenhouse gases can be very local. So measuring them requires a big network, for example. Are the increases due to human activity? Are the increases in temperature and sea level rise and other things due to human activities? Of course, yes. Is the climate warming? Yes. Is the warming in part due to human activities? In part due to human activities? Yes, we saw that already. And what fraction of the warming is due to human activities? 50 to 90% of it is because of human activities. What human activities are responsible for warming? Obviously, increases in greenhouse gases like CO2, methane, N2O, and black carbon particles due to human activities because black carbon is absorbing solar radiation, low albedo. Can we make precise predictions of future temperatures? Not yet. Okay. Global scale temperature warming related directly to increases in greenhouse gases are easily predicted, but if you go to local scales, it becomes harder and harder. Okay. Energy balance on a global scale is done better. Models are good at producing observed warming at global scale, like this. Okay. So this is not a model, this is from observations, but models can reproduce this observed trend very well, but they have a hard time producing these ups and downs. So if you look at annual mean temperature increases with respect to the base period, which in this case is 1951 to 1980, the base period is not always the same. It doesn't make a whole lot of difference, but it's always good to know which base value is used. So before 1940, the temperatures were global mean temperatures were generally cooler, with these year-to-year ups and downs related to things like El Nino, monsoon, and other climate variability known as climate modes, natural climate variabilities. And the smoothing with something like 5 years allows you to see clearly the trend much better than year-to-year variability. It started to bump up around the Second World War and then had few ups and downs, and since the 1970s it has monotonically increased. There is some debate about this apparent flattening here from about 1998 to about 2012 or so, but then it has taken off again, and there is some evidence that the ocean has been taking up the energy. So it's not like there was no global warming, it's just that global warming was not in the atmosphere, but it was in the ocean. Ocean can store tremendous amount of energy. Just 1 millimeter of the ocean with just 0.1 degree considering its area, can store as much energy as we use all year long, for example. Okay, so you have to be sure how much energy there is in the ocean. Okay, so how do we estimate the warming? How much warming, for example, would a 3 watt per meter squared forcing be expected to cause? So you can take the change in greenhouse gas, the increase in greenhouse gases. You can easily compute how much additional energy is being trapped by that increase, and that would be in watts per meter squared. Energy from the sun is coming in watts per meter squared. Infrared energy is going out in watts per meter squared. If they are not in balance, then you look for the increase in watts per meter squared. So 3 watts per meter squared, to calculate how much warming that leads to, we need something called a climate feedback parameter. So this is not very easily calculated. It's quite complicated, but essentially it's how much the climate warms per each watt per meter squared. Okay, so the best estimate we have is about 1.3 watts per meter squared per degree centigrade. Okay, so obviously if you multiply by this, you get degrees, divide by that, you get degrees centigrade, right? So 1.3 watts per square meter per degree Celsius. This means that a forcing of 1.3 watt per meter square would be expected to raise the global temperature by 1 degree centigrade. Okay, so thus we are able to derive theoretical warming that should have been 3 divided by 1.3 should have been 2.3 degrees centigrade. But we just said that the global atmosphere has warmed about 1 degree centigrade since Industrial Revolution, about 1850. Why is that? Because greenhouse gas forcing is positive, but that's the net climate feedback parameter. But there are other factors which reduce the theoretical warming expected just from this sensitivity. You can think of this as the sensitivity of our climate system to radiative forcing. Radiative forcing is anything that changes the balance of the incoming short wave and outgoing long wave at the top of the atmosphere. Right? That's what matters, because that's what is going back to space. Okay? So observed warming is 1 degree because ocean heat storage takes out about half a degree. The aerosols which do the solar dimming and scattering and so on cool by about 0.7 degrees, and surface albedo changes reduce by about 0.2 degrees. For example, if you deforest, you increase the albedo. If you urbanize, you increase the albedo. Even desertification, because of climate change, changes the albedo to reflect more of the short wave. So eventually you reduce from this about 1.3 and end up with 1 degree centigrade. So obviously this is a complicated problem. You have to know how much CO2 you are emitting, how much methane, how much nitrous oxide, HFCs, and where the energy is going into the ocean, in melting glaciers and evaporating the oceans, and what remains in the atmosphere, how much the reflected solar radiation is increasing, how much solar dimming is happening because of pollution, and so on and so forth. But this is a calculation that is constantly done by experts, and numbers are always kept very up to date.